Yes, today I'm going to talk about eBPF. As Sven said, I work at Aqua Security, where we build tools to help enterprises with their cloud native, securing their cloud native deployments. And eBPF is one of the technologies that we're starting to leverage, in particular with a project called Tracy. Now, I have done a talk about eBPF before, but today I'm going to do something new in that I am writing my code, or at least my user space code, with Go today. It's the first time I've done the talk using Go. So that's the new twist that we're going to tackle today. So before I get into the point where I'm going to start using Go and start writing some code, I should probably start by talking a little bit about what eBPF is. Key thing is, it lets you run custom programs of your choice in the kernel. So it's a Linux kernel feature technology that lets you, on the fly, add and change code programs that are going to run in response to events. And you can change them dynamically without having to reboot the machine. So much, much more powerful than writing a kernel module. We've seen eBPF becoming really a hot technology over the last few years because it's so powerful and because you can hook it into so many different events. We're seeing it used in lots of observability tools. We're starting to see it used for security as well. Today, I'm going to talk more about how it works and hopefully give you enough grounding that you can go away and start writing your own eBPF code. Now, if we're going to run some code in the kernel, but as developers, we're usually writing applications in user space. So how do we communicate between user space and kernel? The answer is system calls. System calls provide the interface between user space and kernel. So I can make a pretty good guess that there would be a system call related to BPF, and there certainly is. If we look up the man page for BPF, we'll find lots of really helpful information about what BPF is and how we use it. So first of all, BPF stands for Berkeley Packet Filters. I'm going to use the word eBPF and BPF pretty interchangeably. Historically, it was about filtering network packets, running custom code when a network packet arrived. That's been extended. You can now run your BPF programs in response to lots and lots of different types of events, not just the arrival of a network packet. So whether it's classic BPF or eBPF doesn't really matter these days. But in both cases, you're running code in the kernel and you really, really don't want the kernel to crash or hang. So when we want to run some eBPF code, it goes through a verification step to make sure that it's safe to run. So that's something we'll talk a little bit more about later. So we have some eBPF code that's going to run in the kernel. We have user space application code that, as developers, is normally where we're used to writing code. And there's a system call interface between the two. And I think if we look at the system calls, that can actually be quite helpful for understanding really what's happening when we're talking about inserting code into the kernel. So I'm going to start by using an example. I'm going to use bpftrace. This is quite a widely used tool for running BPF scripts on a system. And so I'm going to show this partly as an example to show the kind of things you can do with BPF, and partly so that we can examine the system calls that happen when we run it. So let's explore some bpftrace and the syscalls it uses. So I have an example that I'm going to use. It doesn't really matter that much what my example is, but in this case, I'm setting up a script that's going to run on a trace point. It's running when we call the sysenter. The sysenter function actually gets triggered for every single system call. So I'm going to run a script every time any process on my virtual machine calls a system call. And it's going to run this script. What that script actually does is it takes it sets up a counter for the number of times each different command makes a system call. So if I try to run that, well, you have to be a privileged user to do it. That kind of makes sense. You don't want every unprivileged user running code in your kernel. So I can use sudo. I just run that for a few seconds, and then I'll interrupt it, and it's going to show us for each different kind of command that's running on my machine, the number of system calls. I mean, that's quite interestingly powerful that we can get to such fine granularity as counting every single system call that's happening on my machine. So I'm going to run the same thing again, but this time let's have a look at the BPF system calls that are being called. So I do that with strace. I'm just going to look for BPF system calls and quit it after a few seconds. And the thing that I want to show you is these BPF system calls that are being called. So we see a few map create, we see map update element, and we see program load. So that tells us something or indicates something about a couple of concepts we need to know about. Those are BPF programs and BPF maps. So we use the same call, but with a different parameter to manipulate programs and maps. So starting with the programs, what are those programs? Well, I mean, they're programs. They run on the CPU. They're essentially machine code instructions. But for BPF, we're restricted in what we can run because of that requirement for BPF code to be safe. Mustn't crash, mustn't loop. So we typically write our eBPF programs in C, a restricted set of C, which we don't use any loops. We always have to check that a pointer is not null before we dereference it. And then we use the Clang compiler to convert it into an eBPF object, a set of bytecode instructions that are going to get run inside a BPF virtual machine inside the kernel. So we're going to write the kernel code in C. We get some helper functions that give us some useful contextual information. So, for example, we can print debugging messages with a helper function. We can get information about the current running command. That's how bpftrace knows which command is running, as we saw in the previous example. There's a few dozen of these helper functions that can help us with contextual information. The other thing I talked about was maps, or the other thing we saw in our system calls was maps. And maps are really how we get information between our eBPF program running in the kernel and user space. We'll come back to a bit more detail about maps shortly. And then the last kind of conceptual thing we really need to know about is the fact that these programs are triggered by an event happening. We saw an example where we run a program in response to system calls, in response to triggering a hook at the entry to the function called sysenter. There are tons of these hooks already predefined. Essentially, every function entry and exit, every system call, every trace point in the kernel, every time a network packet arrives, all of these are possible points where you can trigger an eBPF program. And we also have the term kprobe and uprobe. So kprobe is the entry to a kernel function. A krep probe is the exit from a kernel function, and correspondingly the same for user space. Combination of all these different types of events means we can really run eBPF code in response to pretty much anything that's happening in your Linux machine. So how do we attach the program to an event? And again, I think it's a little bit helpful to look at the system calls that are happening. We're going to not just use the BPF call, but also a couple more system calls. Perf event open, which sets up a trace point. So program load gives us a file descriptor that I've called X here. The trace point comes back as Y, and then there's an IO control event that associates the trace point with the program that should be triggered. So again, we can take a look at that in our BPF trace example. Again, if I just trace out those additional system calls, event open and CTL. And again, it doesn't really matter too much exactly what's happening. I just really want to show you this program load BPF call that comes back with a file descriptor of 9. There should be perf event open. Yeah, this perf event open here, which comes back with a file descriptor of 8. And then here is the IO control that associates 8 and 9 and says, this is the BPF program that I want you to run when we hit that trace point. So loading the program and associating the program with the trace point is something we're going to have to do from user space. Okay. So if we want to write hello world in eBPF, what do we need to do? What do we need to have in place? We know we're going to have to write some C code that's going to run in the kernel and that's going to get compiled by Clang. And we're going to have to write some user space code that gets the tracing, the hello world message from the kernel and displays it. And we can write that, at least in theory, we can write it in any language of our choice. For most of us, we don't typically interact with system calls very often when we're writing user space applications. There's usually some level of abstraction. And in fact, many of us don't even know that system calls exist. We don't have to deal with them on a day-to-day basis. For BPF, there is, we would want a library, a BPF library that gives us a higher level of abstraction over those BPF system calls and things like the perf event open that we just saw. And the library that I'm going to use today is called libbpfgo. We actually wrote this as part of a tool called Tracy that's an eBPF security event detection tool we're working on. And we've isolated the libbpf wrapper. So there's a C library called libbpf, which is a wrapper for the system calls. And libbpfgo is a pretty thin Go wrapper, giving us Go bindings around those libbpf interface. So we're going to write some Go code that uses libbpfgo. And we're also going to write some C code, which we're going to compile into eBPF objects using the Clang compiler. And then the Go code is going to read that object file, get the contents out, insert it into the kernel. So we have an object file that has the eBPF code and the definition of any maps. Talk about maps a bit more later. We have our user space code that's driving our system calls and has the kind of logic around what programs we want to run, what we want to attach them to. When the user space code calls that BPF program load, it sends the program to the kernel. The kernel will verify it, make sure that it's safe to run. And if it is, it will start running it inside this BPF virtual machine. So we're going to build two objects when we've got two different compilation steps. We've got to use the Go compiler, Go build, to create a Go executable. And we're going to use Clang to build the BPF object file. All right. I think we have enough to actually start writing some code. So let's go to my editor. And this is my makefile. It's pretty much exactly what I just showed you on the slide. So we have a Go build step and a Clang step for building the eBPF object. And let's start with the C code. So I'm going to write a function called hello. Takes a context pointer, they all do. I'm going to just do some hello world tracing. So let's say hello GOTOpia. And we'll return 0 exit code. The other thing I have to do is define an object code section. This tells the essentially the object loader what kind of BPF program this is going to be. This is kind of a level of detail we don't need to worry about too much today, but you can use different helper functions and do different things depending on the type of program you're running and the type of event you're attaching it to. So I'm going to attach to a kprobe, the entry point to a function in a kernel. And I'm actually going to run this whenever the system call execve gets triggered. So that's my C code, and let's compile that. So I'm just going to run the make on my BPF object file target to start with. And that should give me an object file that I can look at. Hello, BPF. Okay. And there are a couple of interesting things to look at in this object file. So first of all, it's a little endian machine. I will need that in a moment. This object file is designed, it's compiled to run in a Linux BPF virtual machine. We can see here's the section declaration for the fact that it's running as a kprobe on sysexecv. And here is the function name. So I might say eBPF program. A program is really a function. So that information from the ELF file is what is going to help the Go code know how to insert it into the kernel. So let's write some Go code. Right, I already have a reference to libbpf go here, and I have a convenience function called must that I'm going to use to trap any errors and panic crash if we see any errors. Hopefully we won't hit that. Don't do that in production. Really bad idea. But it'll be fine for demo purposes. So the first thing I'm going to do is I'm going to open this file. I'm going to do new module from file and reading from that object file that we just built. And we want to catch any errors. And I'm going to use a defer call. I don't know if we have any Go programmers here. If you're not familiar with Go, this defer keyword may be new to you. It basically says, make sure that on the exit from whatever function we're in, run this code. In this case, I want to make sure that we tidy up and we close our file at the exit from this function. And just for fun, I'm going to write cleaning up here so that we know when we're exiting from the function. So whatever I call after defer will happen after this statement has been printed. Okay, so I've opened my object file and I now need to load that into the kernel, and that has to succeed. Okay, now I want to get the hello function program and I want to attach it to a kprobe. So first of all, I need to get the program. Got a nice function here to get that program, and we know it's called hello. And we need to attach that to attach kprobe. So I'm attaching it to, yes, the P is my program, and I'm attaching it to the function call that relates to execve. Now, on this particular kernel, the function name is this. Okay, and this could return me an error. So I need to catch that error. Okay. So I've got my object opened. I've got the program from inside that object, and I've associated it with the execve system call. The C code is writing some tracing information whenever it sees that system call, and I need to do something in user space to print it out. And there is a convenient function, trace, there we go, trace print. Now this will basically block and print out whatever it receives from the debug tracing. Okay. So I think we should be able to make this and run it. I have to run it as a privileged user. And hooray, we have the equivalent of hello world. Every time execve is running on this machine, we're getting the trace written out. Now, something didn't happen. And that something is we never saw the cleaning up line that I put. So remember, I've got this here. And that's because when I interrupted the program, well, I just interrupted the program and it stopped. In fact, it was blocked somewhere in here in trace print and got interrupted. If I want to clean up properly, I'm going to have to catch that interrupt, which I can do quite conveniently in Go. And this is also going to illustrate Go channels, which we're going to use a bit in a moment. So I'm going to make a channel. This is a really nice feature of Go channels. And this channel receives one item at a time, and that item is signals from the operating system. And I want to be notified whenever there is an interrupt signal. So that's going to say if someone triggers interrupt, send a message on this signal channel, or actually send the interrupt into the signal channel. And I'm going to block on that here. This is essentially wait until you get an event on that signal and then throw it away on that channel. And the last thing I need to do is send this blocking function off into its own Go routine. This is how Go handles concurrency. This is basically means it's off doing its own thing in another thread, so this won't block anymore. So I haven't done anything very different in terms of eBPF program, but it should now run a bit more cleanly in that if I hit Control-C, we now see our cleaning up message. And we know that things like my defer function will be executed because it will, there's nothing interrupting it before it gets to complete the function. All right, so that's hello world, but it's not terribly useful. In particular, this printk function is writing data to one well-known pipe location on the machine. If I ran any number of eBPF programs and they all called printk, they'd all be writing to the same pipe, which is not very useful for anything real world. So we're going to have to go back and think a bit more about maps. So I mentioned before, maps are the way we can share data between the kernel code and whatever's happening in user space. There are lots of different types of map. I'm going to use a thing called the perf event array. And this is nice, partly because we can write an arbitrary blob of data. So any kind of data we want to write, we can write it into this perf event buffer. And on the user space side, there's a perf buffer implementation that can receive these data blobs on a Go channel. So it's very sort of idiomatic way of receiving data from the eBPF code. Right, so let's use BPF perf event output. So we're going to do that here. BPF perf event output. Get rid of my tracing call. And what does this require? This requires context. We need a map. I'm going to just call it, I'll define it in a second, but we'll call it GOTOpia. I have to pass a flag that indicates it's the current CPU. And I'm going to pass some data. I have to say how big the data is. So let's make things easy. Let's pass some data. We'll just pass a value, make up a value and pass it. So whenever execve gets called, we're going to pass this value into the perf buffer. Just remains for me to define the perf buffer here, perf output, and that is called GOTOpia. Okay. And if I were to make that object and have a quick look at it again. Read elf. Hello. And this time we can see, in addition to the function name, we've also got an object defined called GOTOpia. That's the definition of the map that has to exist in the object file. Okay. So the kernel side is writing this data into my perf buffer, and I need to read it from the Go side. So I'm not going to be using traceprint anymore, but I am going to be using a perf buffer. So we'll call it PB. And we init a perf buffer, and it's called GOTOpia. And I need to pass in a channel for the events that we're going to receive. I'll define that in a second. I'm going to ignore any lost events. Page size that I know works. Okay, that has to succeed. And we have to start, oops, PB, not PS, PB, the perf buffer. And when we get to cleaning up, we're going to stop it. I need to define this events channel. So we'll make a channel. And the type of data that we get from here is a slice of bytes. So that's what we need to receive. And we'll just say some arbitrary length. Okay, so that's set up the perf buffer. We now need to receive these events. I'm going to do it in a Go routine again, which I'll call inline. And we're going to loop reading information out of this channel. So every time data arrives on that channel, it'll get assigned to data, and let's print it out. Got something. Now, we know that it's an unsigned 64-bit integer. So I can convert my slice of bytes, our little endian, we saw that before, UX64 data. Okay. So let's see if that builds. It does. So hopefully this time, every time execve gets called by any process on the machine, it's sending us 64-bit integer. So we're using this perf buffer, but we're not doing anything very useful with that. It's just some number that I've decided to pass. How about we get some information about the current context, like what's the name of the command, the current command being called that triggered this, the syscall, the execve syscall. So we, instead of passing numeric data, let's make this into some characters. Again, a bit of an arbitrary length, size of that data. Okay, so we write it into the perf buffer in exactly the same way. And I just need to change this so that converts my string of bytes, my series of bytes into a string. So now I should be able to say that. So this time, every time execve gets called, we should see the name of the command. And yeah, we can see I happen to have like Kubernetes and Docker running on this virtual machine, so they're spawning quite a few new processes. So this is starting to get pretty close to the example we saw with bpftrace. If you remember that example, well, it was summing up a counter for each different command. So I think that would be pretty easy to implement in Go. Let's so we're going to have a map of the command name, which is a string, and a counter. Make some arbitrary size of that. And instead of printing out the name of the command, we can just increment the counter for that name. Okay. And when we finish, we will loop over that counter and print out the results. So key and the value from my counter will print out the name and the value. Name and the value. Excuse me. Right, have I missed anything there? I think that's okay. So this is still associated with the execve call. Let's see if it works. So we'll just run that for a couple of seconds. When we interrupt it, it should print out the counters. Okay. The last thing we need to do is change the attachment point. So currently we're attached to a K probe at the entry of execve. I'm going to change it so that it's associated with a trace point for sysenter. And as I mentioned before, sysenter gets called every time any system call is invoked. So I need to change that in two places. I need to change the section declaration here. So this becomes raw trace point, sysenter. And I need to change where we attached it here to a raw trace point called sysenter. And with a bit of luck, this is going to recreate that BPF script. So we'll just run it for a few seconds. And then when we interrupt it, we should see a counter. And those counters should tell us how many system calls have been invoked by each of those different commands. So we've recreated that bpftrace command. We've done it in just under 60 lines of Go code and a handful of lines of C. I hope that's given an illustration of the kind of things you could do. Now, obviously, you can attach to many different trace points. I've only slightly scratched the surface of the things that you can do with BPF helper functions and all the different range of contextual information you could then observe and manipulate and pass up to user space. I've had to gloss over lots and lots of details in the interest of time, but the code that I've written is available on GitHub, and I'm really hoping that you have some questions for me.